Next presenter is Yasaman Majd from Electrical Engineering PhD program.
Have you ever what happened if your cell phone or GPS doesn't work correctly when you go to the environment with different temperature or humidity? I guess you wouldn't like it. Me neither. That's why I'm working on the oscillators for timing applications. Oscillators are the important block of your cell phones, computers, radios, and many other gadgets. They help everything to stay in sync by generating clock signals. In fact, these clock signals are the heartbeat of these systems, and we want this heartbeat as accurate as possible with high stability. By stability, I mean the clock signal must not change with temperature, or if it changes, the variation must be as low as possible. To make the oscillators working, we need a power source, energy source, and some components to vibrate. These vibrating components are called resonators. They like to vibrate at a specific frequency, just like a tuning fork. Here on the picture, you can see two types of the resonators. Quartz resonators that made out of the common crystalline material can be found on the Earth, and silicon MEMS resonators that have silicon on that. Quartz one has really good frequency stability versus temperature, but they are big, bulky, and the process of making them is not easy. MEMS, on the other hand, has much smaller footprint, easier fabrication process, but they don't have good frequency stability compared to quartz. So there is a competition between those. To take advantage of a smaller size, easier fabrication process, and of course good frequency stability, I come up with a passive temperature compensation method in my dissertation to compensate the frequency drift of MEMS resonators and achieve stable oscillators. To give you a better picture of what passive compensation method is, consider your MEMS is like a tiny drum that vibrates to make your system work, but it is sensitive to temperature. As soon as the weather changes, it plays the wrong rhyme. To fix this issue, we need a friend who automatically tunes this drum. In this way, whenever the temperature changes. In this way, no matter it's a scorching day or a chilly night, the drums always play the right tune. This is the basic, that's what I am doing in my dissertation. So I choose a material here is lithium tantalate as a friend that has an opposite frequency behavior to what we have in a silicon. So we believe by combining these two materials, we can compensate the frequency drift of silicon and achieve stable resonators and consequently oscillators that can be utilized in many applications such as biomedical, military, communication, and lots of other technologies. Thank you.